to the last session of this day. So first, a quick announcement for the workshop dinner and the lab session. So it's not here, but it's in the marketing team, and you can find the address on the website, and it's also written here. Okay. So the first talk of this session is verifiable encryption from MPC-in-the-Head, and the work is by Akira Takahashi and Validity, and Akira is giving it.
Thanks, Lisa. So this is a joint work with Greg Zaverucha from Microsoft Research. So first, I'm going to introduce verifiable encryption, and then explain how to construct verifiable encryption from MPC-in-the-Head protocols. And then I'm going to describe our optimization techniques and concrete instantiations. So what is verifiable encryption? So as a motivating example, I would like to begin with verifiable key backup across cloud services. So let's say you are a cloud service administrator or user, and whenever you perform some sensitive cryptographic operations inside the cloud instances, perhaps what you want to do is to perform these operations inside some protected environment, such as a hardware security module. So here, hardware security module stores some, for example, ECDSA key pair. And then all the signing operations should happen inside HSM. However, in case of hardware failure or something, you probably want to create a backup for keys inside HSM, and then later recover the backup in the secondary HSM. So one way to achieve this is to ask the secondary HSM to create a public key encryption key pair, and then ask the primary HSM to create a ciphertext under the secondary device's public key. However, because keys should not be reviewed outside HSM, you as a verifier are not entirely sure whether this ciphertext is well formed or not. So one solution would be to ask the HSM to create some zero-knowledge proof, guaranteeing that the ciphertext C correctly decrypts to discrete log with respect to some public key. And then once you verify, now it is guaranteed that when you transfer this ciphertext to the secondary device, the device can successfully recover the correct secret key. So this is one example, and the verifiable encryption offers a solution to these kinds of problems. So let's abstract the problem. Here, there are three parties: prover, verifier, and the receiver. And the prover holds a secret witness and a public key generated by the receiver. First, prover creates a ciphertext under the public key, and then generates a proof claiming that she encrypted some W that satisfies a certain relation. And then the prover outputs ciphertext C with some phi. And after verifier verifies the proof, the receiver, by running some recovery algorithm, obtains some witness. And in the literature, there are several applications of verifiable encryption, such as key escrow, optimistic fair exchange, group signature, anonymous credentials, and so on and so forth. So what about the security? The security requirements are very similar to zero-knowledge proof. So of course, you should satisfy completeness. If everyone is honest, then the verifier accepts and the receiver gets the right plaintext. It should also satisfy zero knowledge, especially verifier does not know the secret decryption key. So in this case, on a high level, verifier should learn nothing about the what's encrypted by the prover. Validity is somewhat similar to knowledge soundness, but it's slightly different. So here, there's a verifier, and if the verifier accepts a proof phi, the receiver is guaranteed to obtain a correct plaintext satisfying the relation, even if the prover behaves maliciously. So usually these are the design goals whenever you construct a verifiable encryption. So if you look at the previous constructions, so there are some efficient constructions, but there are a few challenges. So, for example, most of the previous constructions are either tailored to a specific relation or public key encryption schemes. And this is mainly because you have to design the zero-knowledge proof for efficiently proving some relation or for giving a proof of plain text knowledge for each particular public key encryption scheme. So on the other hand, the goal of this work is to achieve some flexibility in the receiver's public key encryption. We'd also like to minimize assumptions. For example, if you encrypt the discrete log using the ELGAMAL public key encryption scheme, probably you would like to avoid additional assumptions defined over pairing-friendly groups. So in this context, our results can be summarized as follows. So in this work, we show a generic compiler that turns MPC-in-the-Head zero-knowledge proofs into verifiable encryption scheme. And this approach, with this approach, we can instantiate a verifiable encryption based on many existing NGCP secure encryption schemes and several recent MPC-in-the-Head protocols that I'm going to explain soon. And one nice feature is that we can entirely avoid the proof of plain text knowledge. And then we have two concrete instantiations. One is a verifiable export of a discrete log private key. And this can be achieved using a simple distributed key generation in the head protocol that we have on the paper. Also, with another approach, we can also achieve a verifiable encryption of AES private keys. But in this talk, I will mostly focus on the example instantiation based on ZK, because this is a very nice canonical and simple protocol. So hopefully this is going to convey the main idea of this work. So, okay, so how do we construct a verifiable encryption? So a quick recap of MPC-in-the-Head. So MPC-in-the-Head is a zero-knowledge proof for any NP relation. And this was originally proposed by ICOS 2007. And then since this work, there have been many efficient constructions. One nice example is a picnic post-contact signature schemes. And also there are, in recent years, there have been a bunch of practical MPC-in-the-Head based proofs. And some of them are very such as Banket, BB2, Leglogs, and so forth. In this work, mostly we focus on analysis on ZKBoo, KKW, and Banket. So what is how does it work? So there are again two players. So first, a prover holds a witness and secret shares of the witness. And then she distributes shares of witness to some sort of imaginary parties in that case. And then executes multi-party computation protocol, computing some function. And after executing MPC, each party obtains some view. Then the prover commits to each view using some commitment scheme. The challenge indicates which party's view should be hidden. So for example, if challenge I is equal to 3, it means that the prover should open view 1 and the view 2, and view 3 is kept hidden. Then the verifier checks that the commitment openings are correct, and then also open views are consistent with each other. So that's a very basic blueprint of the MPC-in-the-Head construction. And here's one important observation. So as you can see here, of course, commitment 3 is not open yet. But of course, once you review the remaining commitment, it immediately leaks the secret witness because the remaining view contains the remaining share of the witness. So once you have entire views, you can immediately reconstruct the witness. And this is the user observation when you prove online extractability or straight line extractability of MPC-in-the-Head zero-knowledge proofs. So the main idea of our approach is really, really simple. So basically, we just replace the committing function with some public key encryption. And then in particular, we use some in-CPA secure public key encryption as a commitment. So it turns out that with this approach, the MPC-in-the-Head proof itself is already a verifiable ciphertext. So it is easy to see why. So now in the verifiable encryption setting, there's a third-party receiver. And this receiver knows the secret encryption key. So he can successfully recover the remaining view by just decrypting the remaining commitment. And then this helps him reconstruct the witness from all the views. So that's a very simple observation. And then what about security? So completeness and zero knowledge are relatively straightforward. So of course, as I already explained, once you have all views, the receiver can recover the witness. And what about zero knowledge? So once you have an in-CPA security of encryption scheme, this already implies that the commitment obtained by encryption function is already computationally hiding. So this gives you zero knowledge, computational zero knowledge. However, for validity, we have to be a bit careful. Here's why. So it turns out that the in-CPA security of public key encryption is not sufficient if the correctness of the encryption scheme is not perfect. So here, the prover is malicious. So this means that there's no guarantee that prover samples the randomness from the right distribution. The prover could potentially play with the distribution of the randomness in such a way that the decryption failure gets caused for some ciphertext. So of course, in case the randomness is biased, it might be that the receiver obtains the incorrect view, and then eventually the receiver fails to recover the right witness. So this actually breaks that. And this is in particular relevant to recent efficient post-quantum public key encryption scheme, because such as lattice-based schemes or code-based schemes. So they set a parameter such that correctness is only statistical to achieve some efficiency. So in order to retain validity, we assume some additional property, which we call undeniable public key encryption. So relatively, it's easy to understand. If the adversary just submits the tuple of ciphertext, message, and randomness, and then we require that the adversary cannot come up with such a tuple that causes decryption failure, but the re-encryption of the message and randomness leads to the ciphertext. And this is actually, the similar notion actually appeared in the literature. We call it committing encryption, and we call it undeniable encryption as it's an opposite notion to the so-called deniable encryption, which is usually harder. So can we achieve undeniable public key encryption in a generic way? So the answer is yes. The good news is that we can actually show that simpler variants of the Fujisaki-Okamoto transform, which generically converts CPA secure encryption scheme to CCS secure one, already retain undeniability in the random Okamoto model. And actually, the full-fledged Fujisaki-Okamoto is not needed. We can actually simplify a bit. But I'm going to into detail. But the thing is, it's actually easy to retain the validity essentially for any public key encryption scheme. So this approach works for post-quantum schemes. Okay, so these are the basic ideas. So I want to talk about some optimizations. So of course, even though I said the prover commits to the entire view using the encryption scheme, it's actually not necessary. We can only ask the prover to encrypt the witness shares, and then the prover can just commit to the rest of the proof strings using the use of committing functions such as hash functions. And this gives you a much shorter proof size. And also, once the proof is verified, verifier only needs to output the partially reconstructed witness and the remaining ciphertext. But one drawback is that in order to achieve the negligible soundness error in the MPC-in-the-Head setting, you need to repeat the protocols in parallel many times. So this also implies that in the verifiable encryption setting, the verifier has to output all the ciphertext from all the parallel repetitions. So this is a bit wasteful. And also another observation of ours is that actually once the verifier verifies the proof, you can safely discard some of the ciphertext. So this random subset method, in this method, the verifier just randomly samples a subset of some size n, and then outputs the subset of ciphertext from some parallel repetitions. And in this way, the receiver only needs to try to recover the plain text from a subset of the parallel repetitions. And it turns out that you can safely do this without sacrificing the validity. So the impact is sometimes significant. For example, that if you instantiate the verifiable encryption with zkBoo, so if you look at this graph, then the original number of parallel repetitions is 219 in order to achieve 128 bit security. But actually, you can safely discard more than 2/3 of the ciphertext while keeping the 128 bit security. So this significantly reduces the ciphertext size. Or if you want to further optimize the ciphertext size, you can even increase the number of parallel repetitions. And in this case, you can discard more ciphertext and then achieve a smaller. So there's some trade-off between the proof size and the ciphertext size. Depending on what you want, you can flexibly configure with this approach. Okay, so we have some concrete instantiations. So once you apply this transform, you get a bunch of interesting corollaries thanks to the previous works. So of course, ICOS is already a zero-knowledge proof for any NP relation. So you can verifiably encrypt the witness for any NP relation. And using zkBoo, KKW, or Limbo, we have more practical proofs for any circuit. For example, you can verifiably encrypt deep private keys or hash function image and so on and so forth. Banket is also another nice example. This is a special, highly optimized proof system for AES circuit. So using Banket together with some post-quantum public scheme, you can also verifiably encrypt the AES private keys under post-quantum secure public encryption scheme. And I don't have time to talk about the distributed key generation ahead. This is one new protocol we have in the paper. It's a very simple protocol. Essentially, you ask the prover to run passively secure distributed key generation in the head. And it turns out that you can easily achieve verifiable encryption of discrete log private keys with this approach. And we have not implemented these protocols yet, but we gave some performance based on the performance benchmarks for each building block from the literature. So for example, if you encrypt the AES private key using Kyber lattice-based public encryption scheme, so the ciphertext is relatively large compared to the one instantiated with Elgamal, but still it's within somewhat acceptable and the prover and verification time is reasonable. You can also verifiably export technique private keys, or using the DKG-in-the-Head protocol, you can also verifiably export the ECDSA private keys. So the performance okay, but I wouldn't say that maybe depending on the instantiation, there might be more specialized and highly efficient protocols. If you can design a very efficient zero-knowledge protocol for some of the combination, you might achieve a better one. But again, the point of this work is to achieve flexibility and some general. Okay, so to conclude, in this work, we have a very versatile framework of verifiable encryption for a large class of relations and public encryption tools. And also, we observed there are some interesting connection with online extractable zero knowledge and the commit and proof zero knowledge. For example, some early construction of verifiable encryption looks somewhat similar to the transform that achieves the online extractability for zero knowledge proofs. Or you could see the MPC-in-the-Head based verifiable encryption as some of the commit and proof type MPC-in-the-Head protocols. Although the details are a bit different, but the ideas and the motivations are somewhat similar. So there seems to be some interesting connection between those notions. And then the performance is okay as long as the efficient MPC-in-the-Head exists for a particular relation. And we expect the possible improvements will happen similar to the improvements to MPC-in-the-Head signatures. There are potential interesting future directions. In this work, we mostly focused on analysis of MPC-in-the-Head proofs. But if you can apply a similar idea to essentially any interactive oracle proof type systems, and to achieve a verifiable encryption, that's interesting. And then we are also interested in achieving constant ciphertext size. And finally, there might be some interesting applications of a DKG indirect protocol. So that's it from me. Thank you so much for your attention.